Exploring the solar system is a long-standing dream of humanity, but to achieve it, we first need to establish a base on the Moon. The Moon will serve as a pit stop for further missions, allowing us to test technology and gather resources before venturing out into the unknown reaches of space. Before we can build large lunar bases with launching pads and other infrastructure, we need to lay a fundamental shape of construction: the berm, a raised mound of soil-like material that can be used to build the foundation for bigger, complex structures. To build the berms, we will be using regolith, the layer of loose soil and dust on the lunar surface. Excavating regolith will be a critical step in the construction process and needs to be done efficiently. That's where our system comes in, the Lunar Autonomous Regolith Excavator, or LunAR-X for short. LunAR-X is built on a high-traction mobile base, the ClearPath Husky 200. At the front, we have our excavation tool, the bucket drum, actuated by high-torque motors via a belt drive system. To collect and deposit regolith with precision, the bucket drum is attached to a lifting arm mechanism that can raise and lower it using a linear actuator. In addition, we have Intel RealSense D435 cameras that allow the robot to sense the environment. Together, these components make LunAR-X capable of efficiently excavating and collecting lunar regolith. On Earth, wheel loaders are efficient at moving material due to their high traction forces. However, on the Moon, which has only 1/6 of Earth's gravity, high traction cannot be guaranteed. To address this, NASA designed the RASR platform. Inspired from this, we invested time and effort into creating our own bucket drum tool. With its unique design, the drum can excavate when rotated in one direction and deposit the material when rotated in the opposite direction. As the material is deposited, it assumes the shape of a berm, creating a stable foundation for structures. Our loader can collect up to 9 kg or 19 pounds of material per excavation cycle, and that too, completely autonomously. This is made possible by the seamless integration of our localization, mapping, planning, and control subsystem. Without GPS, localization on the Moon proves to be a challenging task. We use a total station to get the absolute position, wheel encoders on our mobile base, to determine the velocity, and an IMU to calculate the orientation of the robot. Upon receiving a task, our advanced task planner strategically breaks down the berm into sections and finds a feasible and optimal sequence of sections to visit, minimizing operation time. For autonomous excavation, our system leverages the tool power feedback to precisely control the linear actuator, lifting or lowering the bucket drum efficiently. To navigate the rover to the desired berm section, we use a hybrid A-star path planner and a regulated pure pursuit controller. To overcome the errors of navigation, we perform visual servoing to command the rover to adjust its position and deposit material with precision. This cycle is repeated until the desired berm is built successfully. Furthermore, throughout the operation, the robot concurrently maps the terrain, creating an elevation map. This allows our system to evaluate the final berm's length and height at the end of the process. While our system has showcased its capabilities in a small-scale setting, we envision scaling it to perform autonomous operations on the Moon in the future. We are Team LunAR-X, and we are here to reshape the Moon.